derivative or none?
This is just first derivative. Yeah. Okay, so we're still doing implicit differentiation.
Oh, that's real nice. I can see the real colors there.
You get to see the real colors. All right. For example, do I need to use a darker color so you can see it?
No,
I can. That's good. Okay. So we're going to say that we are given x squared minus xy plus y squared equals 9. And this is like a perfect implicit differentiation problem because that y is not really solvable. Like we can't really get it by itself. So we're going to do a few things with this. Now this would be like maybe if I were to give an FRQ or something and it had multiple parts and you had to work your way through different things, this could be a potential FRQ question, okay? So there's our curve. If we're going to go ahead and write the general expression for the slope of the curve, what do I mean by that? Find the derivative. Mm-hmm. Okay. We're going to find the tangent lines. Now I'm going to put the S in parentheses because it could be one or it could be more than one. All right, so find the tangent lines for the curve when x equals 0. And then last, we're going to say find the coordinates of the points where the tangents are vertical. Ooh, look at my nails this time.
Oh, that's what my nails look like.
Yeah, they don't look chrome anymore because that was when my nails were blue. Now my nails are purplish, and so they look, I don't know what color that is.
White.
That's not white.
That's like an alien glow in the dark green blue.
Yeah, it's like ghostly blue.
This is what a regular nail looks like.
You're color deficient.
Well, okay, this looks white. Does it look white?
Those are the same exact color.
Are you?
Tristan, do you have male pattern color blindness?
No, not blindness.
All right.
Color deficiency.
So, looking back, we're going to answer part A, which is where they were asking us to find the general expression for the slope of the curve. So we have x squared minus xy plus y squared equals 9. And that means that we're finding the derivative.
2x minus x dy dx plus 5 plus 2y dy.
So 2x, and then
Minus x.
So first times
The derivative of the second.
the derivative of the second, which is 1 dy dx.
Plus.
So we have to be careful because this is subtraction, right?
Yes.
So yeah, so I'm going to go ahead and put parentheses. Are you guys okay with that?
Yes.
So anytime I have the product rule and I have a minus in front of the product rule, I like to put whatever I get for the product rule in parentheses to make sure that I minus both terms. Okay, so You can do it in your head if you want, but you could make mistakes, all right? So first times the derivative of the second plus
Y.
the second times the derivative of the first, all right, plus
Y.
2y dy dx equals 0. I feel like you're passenger seat driving. He's like sitting up here doing the example faster than I am. All right, so I've got 2x minus x dy dx minus y plus 2y dy dx. Okay? Okay, move those over to the other side. So I'm going to keep the negative x dy dx, and I'm going to keep the 2y dy dx. And then on the other side, what do I get now that I've moved these over? So negative 2x plus y. If you don't like the negative being in the front, you could write y minus 2x. That's fine. Or you could do negative 2x plus y. It doesn't matter. All right, now what do I do? Well, I didn't skip the 2 steps. Yeah, I wrote it. Anyone know why I write all my work? So you can see it, and then also because you're less likely to make silly mistakes if you're writing out all your work. Okay. Yes. Yeah. Okay, so I'm gonna.
Can you combine steps in FRQs? That's fine, right?
Yeah, on FRQs you need to show the setup work because the setup work often gets a point, and if you don't get that point, you're often not eligible for the points after that. So if you skip the setup, it doesn't matter if you get anything else right because you can't get that point, and then you can't get anything else.
I don't like that my Y's and X's flipped.
If they like.
I took a factor of -1 out of both of them just to make it.
Yeah, you can do that. So if you take a negative out, then you'd get 2x minus y over x minus 2y. Yeah, that's fine. They're both good.
You also could do Y minus 2X over
Yeah,
2Y minus X.
anything you did is totally fine. You guys are good. You're right, and you're still right. Yeah, okay. All right, so now what we want to do is part B, which is find the tangent for the curve when x equals 0. So if I want to find the tangent for the curve when x equals 0, what do I need to do? So we found the derivative. What do I need to do with x equals 0? Plug it in. Now, normally we would say if I want to find the tangent line, I just take the derivative, I just plug 0 in. However, we have an issue. Yeah, we have an x coordinate of 0, but we don't know what the y coordinate is. And to find the tangent line, we have to have an x coordinate and a y coordinate. So we're going to go back to the original equation, and we're going to plug in 0 for x and see what our y values are. And then we can plug them into the derivative. So this is part B. The original equation was x squared minus xy plus y squared equals 9. And we're going to plug in 0 for x, and we're going to solve for y. So what do I get? Y squared equals 9.
So it's plus or minus 3.
Y equals plus or minus 3, because when you square root, you always do a plus and a minus. Yep, so you're going to have 2 tangent lines. Okay, now when we do this work, we are going to say, I'm going to take dy dx, and I'm going to evaluate it. That's the notation used to evaluate it at the point 0 for x, 3 for y. And then I'm also going to take dy dx, and I'm going to evaluate it for 0 for x and -3 for y. So that's the notation that we show when we're taking a derivative and we're using this type of notation, that dy dx. That's how we show that we're plugging in an x coordinate and a y coordinate. Does that make sense? Okay. So now we have our derivative. Which form of the derivative do you guys want me to use?
Do you do the y minus 2x over 2y minus x.
Okay. So if I do y minus 2x over 2y minus x, and then y minus 2x over 2y minus x.
I'm just saying. What's 1/2?
3
Yes. Yeah, because if you solve
over
it, if you solve it
6.
without putting the variables in, you get out 1/2. You don't even have to put 3 in for y.
Don't ruin it for me.
Oh.
Oh my gosh, you guys, it's 1/2 and 1/2. They're the same.
Woo!
Toby said it
Who would've
first.
known?
That was crazy. That was crazy. Who knew it?
They're both 1/2.
They're both 1/2. Tristan, good job. All right, so let's go ahead. Are we writing a tangent line or are we writing tangent lines? We're writing 2 of them. Okay, so for the first one, we're going to write y minus 3 equals 1/2 times x minus 0. And then for the second one, y plus 3 equals 1/2 times x minus 0, and I'm done.
Did you just write x?
Yeah. Who wants to think?
Me.
I whispered it, but he's the only one who heard it. That's awkward. All right. So for the next one, the instruction said to find the coordinates of the points where the tangents are vertical. So we're going to start with the derivative, and we liked the 2y version, right? Or y. So dy. Okay, you guys liked this version, right? Okay.
Yes. Why don't you? What don't you like about that version?
Okay.
I agree with Steven.
So to find a vertical tangent line, yeah, so our derivative gives us the slope of a tangent. And if we want a vertical tangent, then we have the slope of a vertical line, which is undefined. Okay? So we need our derivative to be undefined. And if we can find the point where it's undefined, then we can find the vertical tangent. If you wanted to find a horizontal tangent, what would you want your derivative to equal? Yeah. So vertical tangent will make the bottom equal 0. Horizontal tangent, we would make the top equal 0. Does that make sense? Okay. So I'm going to take the bottom, 2y minus x, I'm going to set it equal to 0. And when we do this, we're trying to solve for an x-coordinate and a y-coordinate, right? And we're trying to find the x-coordinate and y-coordinate on the original curve that would make a vertical tangent happen, okay? So this equation right now, I get 2y equals x, and I have to go back to the original curve. So I have to go back to the original curve, and what I'm going to do is I'm going to take all the x-coordinates out of the original curve, and I'm going to plug a 2y in for them. And I'm going to do that because then I can solve for x. Okay, so the original curve said x squared, so I'm going to go ahead and do 2y squared minus x times y, which is 2y times y, plus y squared equals 9. It wasn't that funny, but it was kind of funny.
That sums up this whole experience.
I mean, yeah, it's good. It was good. All right. So if we look at that, be really careful with your exponents and all that stuff.
So then you look at, I think 4y squared minus 2y squared plus y squared equals 9.
Okay.
3y squared equals 9.
Yeah, exactly.
So 4 minus 2 is 2 plus 1 is 3. Okay, so 3y squared equals 9. Then what do I do?
Then you divide both sides by 3, and then you square root both sides.
What?
No, if it's already under a root. No, if we put a root on.
Yeah, if we square root, then we do the plus minus. So since we're square rooting each side, we're going to say our answer is plus or minus root 3. So how many times are we going to have a vertical tangent? Twice. Okay, so we know the y coordinate of the vertical tangent. How do we find the x coordinate of the vertical tangent? Yeah, now, yeah, so you have two options for plugging in that y. You could take that and plug that into the original equation if you wanted and solve for x. You'd have two x's left over to solve for those. Or you could just plug it in back here because that's a little bit easier, right?
Yeah.
Okay, so if we plug it back in right here, yeah, then we're going to say for our first option, I'm going to use the negative root 3. And if I do 2 times negative root 3, what do I get? Negative 2 root 3, okay. And then if I do the version where I'm plugging in a positive root 3, oh, please don't do that. And if I'm going to plug in a positive root 3, what do I get? Positive 2 root 3, okay. So when we worked through that question, we had never done anything like that before. But did you notice that the vocabulary words that we've learned before kind of helped us talk our way through the problem? Okay, so even if I hadn't done this example in front of you, using what you've learned in math before, you technically would have been capable of the problem. You probably just wouldn't have liked it very much. It would have made your brains hurt a little bit. Okay, there are a lot of steps, yeah. All right, so the plan for right now, you're going to go back to your assignment from yesterday. You should have done 1 through 10 for homework last night, in addition to watching the video. And now you're going to go through, you're going to do 11 through 14. We are going to save the AP problems for over the weekend. Okay? If you are done, then you're good. Then I can give you the next assignment to start working on. Okay? So 11 through 14, that's what we're working on right now. If you are done and you are ready for the next assignment that has your second derivatives, I can hand that out as well. Okay? So 11 through 14, that's what we're working on. Answers are up for 11 through 14, so you can check them.